My name is Jagadish, and I'm from the Australian National University, and I'm going to chair this morning's session. We've got three excellent speakers in this morning's session, and the first speaker is Professor Bivas Saha from Jawaharlal Nehru Center for Advanced Scientific Research, and he did his PhD from Purdue University and worked as a postdoctoral fellow at University of California, Berkeley. Now he established his own research group at JNCSR, and he is leading the Photonics and Polaritonic materials program. And then he's going to tell us about Polaritonic material platform for tunable nanophotonic devices. Bivas, please.
Yeah, thank you so much, Professor Jagadish, for this nice introduction. So let me first thank Professor Tony Chitam for giving me this opportunity. My thanks also to Professor Rao, Professor C.N.R. Rao, for all the constant encouragement and support he has provided. So the title of my talk is Polaritonic Material Platform for Tunable Nanophotonic Devices. Now let me start with a very well-known, but perhaps a little less appreciated fact about the fact that materials and their role in our civilization. Materials have always been the basic building blocks of all the ages that we have seen. Either it's a Stone Age, Bronze Age, Iron Age, Industrial Age, or today's the information technology era. Of course, today's information technology era is dominated by silicon. Just like in any of these ages, the most dominant material was something like bronze or iron in many ages. So if we look at the today's silicon technology era, and if I plot basically the operating speed of devices and critical device dimension, starting from 1950s, where this era has started. With the initial days, the transistor sizes were quite large. With time, transistor sizes have shrink and shrink and shrink, and today we are basically leading all the electronic devices that we deal with. Their transistor sizes are of the order of, say, 5 to 7 nanometer. While this progress has been remarkable, one of the things that we don't always pay attention to, that the speed of the transistor has pretty much remained as constant. When I first bought my laptop, the speed of the clock speed was about 1.7 or 1.8 gigahertz. And today, if we try to buy a laptop, the speed is again about 3 gigahertz. So the speed hasn't changed much. And at the same time, if you look at the dielectric photonics, which is another basic component of long-distance optical communication, they pretty much work with the same principle after its invention in 1960s. So if in this chart, if we look at the device operating speed and critical dimension, the biggest limiting factor, which basically impacts all electronic and optoelectronic devices, is diffraction limit in one case, which basically says you cannot go below a certain wavelength of light, and RC delay, resistance-capacitance delay in electronic side, which basically doesn't allow you to increase the speed beyond a particular point. So how to address it in future? And that is where these polaritons or polaritonics basically come into picture. So what is polariton? Now, polaritons are a hybrid quasiparticle that is formed when light very strongly couples with electric dipole that are present in a material. They have a speed of light, and the confinement basically they have at the nanoscale dimension. So light, as we all know, has a huge spectral range. It starts from UV visible all the way to far IR to terahertz spectral range. So if you really want to excite polaritons, you really have to find different sorts of excitation or dipoles that are present in the material to achieve this. Now, fortunately, in materials, there are many types of dipoles that are present. For example, there are excitons, plasmons, optical phonon vibration, polar phonon vibration, Magnon-Cooper pair, etc. And last time I checked, there are about 71 different types of dipolar vibration that are present in the material, which people have used to generate this polariton. Now, usually they are defined as whatever the excitation is. For example, if you strongly couple light with an exciton, you basically form exciton-polariton. If you couple with plasmon, you form plasmon-polariton, and so on and so forth. Now, why it is important? It is important because pretty much all the emerging technologies or important device technologies, which are categorized as quantum technology, energy technology, and healthcare technology, basically can use or already use polariton and their applications. In the visible spectral range, for example, there are many, many examples. Some of it I'll show. For example, solar energy conversion, lasers, local heating, that really benefit from polariton and polariton physics. In the infrared spectral range, whether it is optical communication or molecular fingerprinting or night vision devices, many of them actually utilize this Polariton. So before I go ahead and explain all the details about Polariton, let me just give you a 2 or 3 slide summary of optical properties in a material, because that will be important when I discuss the results. Now, how do you define the optical properties of material? Most important parameter that is used to define optical properties of material is by dielectric constant. Or some people may use refractive index also. It doesn't matter, because dielectric constant and refractive index are related to each other. Now, what is dielectric constant? Dielectric constant is basically the ability of a material to polarize given a particular electric field. So this epsilon1 basically gives you the strength of the polarization. Higher the epsilon1, higher is the strength of polarization. And this imaginary part, which is epsilon2, it's actually optical loss. In other words, this is pretty much the light you lose because of absorption and some other phenomena. Now, what are the characteristics of dielectric constants? If I take a glass, for example, window glass, and if I shine visible light in it, there is absolutely nothing in the glass. There is no vibration, nothing, no electron, nothing, which can interact with the incident light. And that is why light pretty much just goes through. And that is why you see a perfectly flat, very low value of epsilon1, and pretty much zero loss. So that is dielectric. In the case of metal, things get much more interesting, because metals have these all free electrons. And when you shine light on a metal, they start oscillating opposite to the electric field. They impede the electric field, and as a result, light basically cannot go through metal, and they reflect back. And the frequency at which it reflects back, or maximum frequency at which it reflects back, is basically known as the plasma frequency, or in some case, in some approximation, it is also known as epsilon near zero frequency here. And the pretty much Drude model works pretty well in explaining the optical properties of metal. Now, just like you can have electrons in a volume plasmon excitation, you also have electrons on the surface of the metal. And if you shine light, and if you are careful that you give enough momentum to this because the surface Plasmon-Polariton band basically lies to the right side of the light cone. So basically, you need an extra momentum for light to couple with the surface polaritons. Basically, you can also excite the surface Plasmon-Polariton modes. So one of the things that you always have to worry, or always have to make sure if you try to excite polaritons, any type of polaritons, is that you always have to match the energy, the momentum, and the polarization of light with that particular excitation. And that is why traditionally, or at least a simple way of exciting surface polariton is just by putting a high dielectric constant material, which is diamond in most of the cases, on the surface of a metal to excite the surface polariton. Some people also use nanoparticle to excite the surface Polariton resonances, and they basically offer a way of confining light below the diffraction limit, and at the same time, you can increase the electric field by many orders of magnitude with this principle. Similar to Plasmon-Polariton, there is also other type of polariton. I'll just give a brief description of phonon-polaritons. If you have a polar dielectric media, for example, you have a magnesium oxide, silicon carbide, things like that, you have all this optical phonon vibration. And because it's a polar dielectric, the electric field basically splits the LO and TO phonons. And in between the LO, TO phonons, there is again a highly reflecting region, which is known as the Westerhall band. So it is a dielectric, right? You can put a multimeter and you get zero current, but optically, it's a metal in this spectral range. And light really couples strongly at the TO phonon, and it can also go coupled with the LO phonon in some conditions, basically. So that is another type of polariton you can excite. And just similar way, you can excite probably all types of polariton. The mathematics pretty much remains exactly same, except that some terms in the equation changes. Now, we are a material scientist, so we approach this problem that how can we excite different types of polariton in materials that are high quality and low loss. Because if you lose light, then it pretty much cannot be used for everywhere. So, and we need to do it in the entire spectral range. So ideally, if you find one material that does that all the job, that would be ideal. But we all know that's pretty much not possible. So the next thing that you can do is that at least find the same family of materials so that either nitrides or oxides, so that you really don't have to end up growing nitride oxide heterostructure or nitride sulfide heterostructure that are practically not possible. Now, if we are only to research with it, then that's pretty much would have been it. But if you really look for practical application, then along with the basic optical properties, you also have to be careful that materials that you're working are stable, they are compatible with the existing CMOS technology, and at least you can deposit them in the thin film phase. And that's exactly the reason why there is absolutely no doubt that gold and silver are the best plasmonic materials in the world, but you really can't use it for practical application because they are not stable, you cannot deposit them in the thin film phase, and so on and so forth. So that's where we come in, and what we research on is on transition metals and transition metal nitrides. Now, why? Why nitrides? Because nitride actually gives you a full spectrum of electronic properties. I shall show you. In the nitrides, there are very good metals like titanium nitride. Nitride has these 3,5 semiconductors, which are world famous. And then nitride also has a dielectric, which is the aluminum nitride or boron nitride. So it offers you a tremendous spectral variation of different properties in nitrides. Nitrides are known to be corrosion resistant, mechanically tough and hard. And they also offer potential acoustic impedance mismatch, which I'll come back later, and growth conditions which are pretty much reasonable to achieve in the lab. So what I shall try to show in this presentation is how we use nitrides and different sorts of dipoles that are present in the nitrides to excite this Polariton resonances, starting from the UV visible spectral range to pretty much far IR, long to far IR spectral range. So let me start with the visible spectral range work. We all know gold and silver were the best plasmonic materials, and but we have ended up developing titanium nitride and hafnium nitride as an alternative to gold and silver in the visible spectral range. Now, this work started when I was a student. Titanium nitride looks like gold, but there are optical properties still needed to be established. So we have shown previously that titanium nitride has an ENZ frequency, or the crossover frequency, at around 500 nanometer, and that resembles like a gold. And we have shown many other applications at that time also. But one of the questions was always that titanium nitride had a high optical loss. So how to get around this? So one of the challenges, one of the ways we have get around this initially when we started our independent group is by depositing high quality epitaxial thin film of titanium nitride with molecular beam epitaxy. And when you deposit it, because you really get around all the loss, all the scattering events, inelastic scattering events with defects, you can see if you focus this red curve, the titanium nitride today have almost comparable, or in some cases lesser, optical losses compared to gold. And we have used it for many other property demonstration also, but one of the application, real application, and I shall show it again later, is that we are trying to develop solar mirrors. Now, in case of solar mirror, you really want to reflect the entire solar spectrum. So if you try to use titanium nitride, or we try to use titanium nitride, there is a problem. And the problem is the solar spectrum shows a peak at around 500 nanometer, and titanium nitride's ENZ frequency is also 500 nanometer. So that practically means that a huge portion of the light in the UV or visible range, which we cannot reflect with titanium nitride. So we really had to move to a different system where we can push the ENZ much deeper into the UV spectral range, and the only way you can push the frequency deeper in the UV spectral range by increasing the carrier concentration. So the choices were not that difficult. You just go below the periodic table from titanium to hafnium nitride to zirconium nitride, and their inherent high carrier concentration basically should be able to give me a mirror that will reflect the entire solar spectrum. So again, we grow them with high quality magnetron sputtering, but ultra high quality magnetron sputtering method. These are perfectly epitaxial, nearly single crystalline film. So we have, from structurally, we have tried to make sure as good a crystal quality that we can achieve. And then when you look at its optical properties, if you see this reflection spectra as a function of wavelength, the solar spectrum is presented in the background. You see the green one is basically the silver, and this hafnium nitride and zirconium nitride are pretty close to silver. And that's exactly the reason why silver is still the best, 95% of the solar reflector, but hafnium nitride, zirconium nitride, they show 93%, 94% solar reflection, which is pretty good and pretty large. We also looked at this, this was the specular reflection at one particular angle of incidence, and solar reflection basically integrate over the solar spectrum also shows very high solar reflectance of 90%. Infrared reflection, as you can see, is about 95%, perfect flat line, and this is true for all angles of incidence, basically. So that is, in that sense, it's very good. Now, initially we thought, we are not sure that we would be able to make such a good solar reflector, because although you can choose a plasma frequency, you can make plasma frequency at a particular wavelength by doping a certain range of carrier concentration, unless you can keep the reflection edge extremely sharp, you can still end up not having a good reflector. And that is why it's extremely important how to increase the sharpness of the reflection. And our students did look at the problem from fundamental perspectives, and we eventually realized that you really have to have a very high tau, which is the relaxation time. Basically, in ideal case, if you don't have any scattering, tau will be infinity, 1 by infinity will be 0, R will be basically 1. So what you need, not only you need a perfectly matched plasma frequency, you also need tau to be very, very small. And you can achieve tau to be very, very small if you basically make single crystal epitaxial films where there are not much defects, and because there is not much defects and not much scattering, you basically can achieve such high sharp reflection edges. Now, we did use it, we did deposit our hafnium nitride, zirconium nitride in industry-compatible substrate also for like quartz, and as you can see, the property don't change that much. So we pretty much now have a very good hold of the fact that in the visible spectral range, we have deposited two materials, titanium nitride, which is sort of a replacement for gold, and hafnium nitride and zirconium nitride, which are sort of a replacement for silver. But visible spectral range is not the only thing. You really have to go to infrared also, because many of the application lies in the infrared spectral range. And in this case, we have come with a new material, well, I shouldn't say new material, a material scandium nitride. Now, what is scandium nitride? Scandium nitride is again a 3-5 semiconductor, perhaps a little less heard because it is a 3B semiconductor, not a 3A semiconductor. It's a rock salt crystal structure. It exhibits a direct gap of around 2.2 EV and indirect gap of 0.9 EV. And like all other transition metal nitrides, it has a high melting temperatures. So we grow scandium nitride again with molecular beam epitaxy as well as magnetron sputtering. They grow nearly as a single crystalline film on MgO substrates, a good quality on sapphire substrate as well. Now, this is pretty much the high resolution transmission electron microscope image just to show the high quality lattice resolved growth of scandium nitride on these substrates. But importantly, when you do the optical characterization, titanium nitride has a large carrier concentration. You can tune the carrier concentration. Because it is a carrier concentration of 1.6, 10 to the power 21, you see the Plasmon resonance of the ENZ frequency at around 1.8 micrometer. 1.8 micrometer is very close to the telecommunication wavelength of 1.5 micrometer. So it's extremely interesting and extremely important. Now, one of the things that metal generally don't allow you to change carrier concentration that easily, but semiconductor does by doping. So just by changing the doping concentration, we can shift the plasma frequency or the ENZ frequency starting from 1.8 micrometer to around 2.3, 2.4 micrometer. So this pretty much covers the short wavelength infrared spectral range, which is technologically extremely important because a lot of security applications use this spectral range. Now, along with the excitation of the normal plasmon, we also excited surface Plasmon-Polariton in scandium nitride by putting a diamond crystal on top of the scandium nitride sample, and you can see this excitation of this surface Plasmon-Polariton close to their relative plasma frequency. And at the same time, we also look at scandium nitride is also a polar dielectric because it's a 3-5 semiconductor. Scandium nitride is 3 plus, nitrogen is 3 minus. So because it's a polar semiconductor, it also exhibits this Resterhall band, phononic Resterhall band, which I was mentioning to you, highly reflecting region between the LO and TO phonon frequencies, and a negative dielectric constant in between this negative region. we also end up exciting the surface phonon-Polariton in this case, which is close to the yellow phonon frequency of titanium nitride. As I said before, conceptually, theoretically, all of these things are pretty similar, except that the spectral ranges are different. For Plasmon-Polariton, we could excite it at, say, around 2 micrometer, but for phonon-Polariton, we are now exciting at 15, 16 in this micrometer spectral range. So how does it compare? Well, if you look at the near-infrared or infrared plasmonic materials, for example, indium tin oxide, aluminum dope zinc oxide, or cadmium oxide, scandium is nitride property is pretty much close to, or in some cases better than many of the materials. So today, it may not be used in some devices, but we can easily foresee a future when scandium nitride can easily find application in this sort of devices, because just remember, in infrared spectral range, there are very little materials which works as good as you need. In terms of phonon-Polariton, the figure of merit, as we call it, and there's a mathematical expression to calculate it, I'm not showing it, but if you calculate the figure of merit, you see scandium nitride is much, much better than many of the other 3-5 semiconductors or polar dielectric media. The basic reason is that scandium nitride has a low band gap, so it has a higher epsilon infinity, and that's basically leads to an extremely high figure of merit. Now, along with this scandium nitride, we have also looked at gallium nitride. Now, I'm pretty sure this audience do not need any introduction about gallium nitride, but let me just say that gallium nitride is the wide bandgap semiconductor 3.4 eV. What is perhaps a little less appreciated is that gallium nitride is also an extremely good polar semiconductor. So if it is an extremely good polar semiconductor, if you take a perfectly flat film of gallium nitride, it would also show a very high quality residual band with reflection reaching almost 1 and negative permittivity within this TO and phonon frequencies. That just comes out of its normal condition, but it's also boring. As an engineer or scientist, we try to find more exciting properties, and the exciting properties that we have developed by nanostructuring gallium nitride. So in our molecular beam epitaxy machine, by changing the growth condition, basically we can go from thin film to basically a nano wall network type of growth, which Professor Jagdish yesterday showing the nano membrane type. So membranes are all connected, basically, nano wall network. And then if you keep on changing the growth condition, in the extreme case, you can also reach a gallium nitride nanowires, basically, vertically standing gallium nitride nanowires. And these are done for its own reason, for different application. But the most important part of this nanostructure is that all of them has very high surface to volume ratio. And that has its application in many places. I'm not going there. But in the context of plasmonics or polaritonics, what is important that if you now measure the reflection spectra of these nanowires or nano wall networks, you see instead of finding a rectangular shape, theoretically well-defined reflection spectra, you see a trapezoidal shaped reflection spectra. Now, what does it mean? Well, it means that close to the yellow phonon frequency, the reflection has gone down. That means absorption has gone up. Because the transmission is 0, we have a backside metallic plate. So if the absorption has gone up, what is that absorption and how is it impacting these optical properties? That is what we figured out in this case. But before I go to the theory behind it, let me show you what happens in case of nano rods. The previous one was a nano wall network, and this one is a nano rod. So in case of nano rod, the effect is even more drastic. The decrease in the reflection is even more drastic. So now let me explain what really happens. I'll not go to the mathematics behind it, but physically what happens is that in these nanostructures, you have very large surface to volume ratio. If you have a large surface to volume ratio, that pretty much means that you have a large surface phonon excitation going on also. And light can exactly, just like it couples with other type of phonon modes, it can also couple with the surface phonon modes. When it couples with the surface phonon mode, and depending on certain geometry, certain depolarization factor, so on and so forth, you can excite this absorption resonances close to its yellow phonon frequency towards TO phonon frequency. Now, given that our nanowires are vertical, this absorption resonances occur close to the yellow phonon frequency, and because this absorption, you see the reflection pretty much going down and giving you a trapezoidal shape. So the nanostructuring basically offers you a new possibility to engineer the optical properties of gallium nitride nanostructures, which are pretty much industry used. So if you want to achieve some application, you can do it without much changing the growth condition or fabrication techniques, growth process or fabrication techniques. Along with the Plasmon-Polariton, along with the phonon-Polariton, we have also looked at Plasmon-Polaritons in gallium nitride nanostructures, because just like you had, if you have a lot of surface carriers, then you have a lot of surface vacancies and surface carrier also, then that gives you carrier concentration, very high carrier concentration of the order of 3.2 to 4.5, 10 to the power 19 to 20 orders. And if you really look at measure deflection, you can also see you can excite this surface Plasmon-Polariton also. And their wavelength can be tuned from near IR spectral range to pretty much long wavelength IR spectral range as well, as you can see in this case. Now, finally, let me come to another example. Now, this example is not nitride, but it will connect to what we were trying when we were developing this visible range plasmonic spectral range. And that is a project that we worked with in collaboration with Russell Kaima and RAC-NOR company. And that is development of metamaterial, which will serve as a radiative cooling, basically. Passive radiative cooling. Because in high summer, pretty much everything heats up. And when it heats up, it makes it very, very hot to even touch it. It turns out that nature has already figured it out how to basically radiatively passively cool, because there is a Saharan silver ant, one of the smartest creatures on the planet. It survives in the Sahara Desert at 50, 60 degrees centigrade temperature, because you see there is a silverish coating on its surface, which basically helps it to reflect the entire solar spectra. At the same time, it has certain fibers in its body, which basically emits in the infrared or atmospheric transmission window. So this is one of the inspiration from nature we use to design this passive radiative cooling. But not just this, Iranians have figured out a long back, Persians have figured out from a long back, this Iranian ice houses where they used to make ices in those desert heat, basically. Now, what I'm talking about, so let me explain more clearly. The surfaces, interfaces, our building, roofs, everything heat up because of heating from the sun. And sun has a solar spectra of around, say, 200 nanometer to 2000, say, 500 nanometer. And that basically makes the surface really hot, at least 15, 20 degrees above the ambient temperature. So we were asked to design a radiative cooling solution which will cool these surfaces 15 to 20 degrees below the ambient temperature. But more importantly, it has to be stable, it has to be reliable, environmentally friendly, and more importantly, it has to have very low cost and very easily solution processable. So the physical principle, scientific principle is very simple, as I explained. If sunlight is giving you the heating, you make sure that you reflect the entire solar spectrum. You don't allow anything to heat up your sample. But that's not going to solve your problem, because there will be residual heating, and that will increase the internal temperature of the material, and that also you need to emit, and you can only emit at the atmospheric transmission window. Atmosphere doesn't allow you to transmit everything from in the entire spectral range. It only allows you to transmit from, say, around 8 micrometer to 12 to 13 micrometer in this spectral range. So we had to come out with a solution which is solution processable, low cost, and that gives you high solar reflectance and high infrared emittance. So and that is why we were working on zirconium nitride and hafnium nitride in the beginning. If you now can, if you can now think in that way. But the solution that we come with is basically nanoparticles of dielectric, for example, MgO, and that is made in a nanocomposite with some polymer matrix. So MgO PVDF polymer matrix. This is basically a polymer matrix between MgO and PVDF. You can solution process it, spin coat it on any surface and substrate that you are looking at. So if I show you the reflection spectra, as you see, the MgO PVDF, it is really high reflection spectra. I think the total reflectivity, solar reflectivity is around 96.3%. With respect to commercial paint also, it has very high. The infrared emissivity is also close to 1 in this wavelength range here, and that basically arises from the stretching and vibrational bond, stretching and MgO stretching frequencies and molecular vibrations from the PVDF also. So this gives you a high solar reflectance and a high infrared emittance. Now, does it work in real life? And that is what I want to show you. This is a real-life experiment done at the Sheikh lab in JNCSR on the terrace of it. So we have two basically samples. One is the real sample, one is the reference sample. So we first tested what really happens, what is the cooling efficiency when you test it between a reference sample and a real sample. You see, this is the top one is basically the solar intensity on that particular day. And this is time. Basically, we're starting to measure at 9 o'clock in the morning, run it up to 3, 4, or 5, 4:30 p.m. The silicon here, or the sub-ambient temperature, is approximately on an average 7 degrees higher compared to this MgO PVDF coating temperature. So we have developed a radiative cooling technology which doesn't use any power, which is passive in nature, that really cools surfaces around 7 degrees on an average when you don't compare it with another coating. You just leave it, compare with something like unintentionally put surfaces. And we also measured this cooling efficiency or cooling power, and that is around, say, 100 watt per meter square. So we are very happy, but then immediately there was a realization set in that there are already commercial paints out. How does your paint compare with those commercial paints? Now, what we did is that JNCSR, I'm sure many of you are there in campus, some of you, I'm pretty sure, come and visit us. Many of the buildings actually have white paints in JNCSR. We went to the civil department and asked for this paint slightly, and we used our paint and compared it with this commercial paint, basically. So with respect to the commercial paint also, you see our paint cools on an average by 3 degrees C and a maximum cooling of around 5 degrees C. So these numbers may sound a little small, but then just think about it. These are the coating we have developing in the lab, starting from the scratch, and I'm pretty sure with more and more, with further time, we can improve more on this. So with that, let me finish. My main message in this talk is that nitrides, which I showed most of the cases, can serve as a host for plasmon, phonon, and all sorts of polariton in the entire spectral range. Some of it are already commercialized. For example, in heat-assisted magnetic recording, titanium nitride is strongly being used to develop local heating cases. But in other cases, we're pretty sure with coming days, there will be many more applications coming up. So with that, let me end. But before I end, let me show you this picture. I joined JNCSR about this same time, 2019, when I first came in Russell Kaima once before. That time we had a very small lab, but thanks to the generosity and help from His Highness, we work in a Sheikh lab. We have established many facilities, and today many of our students are doing extremely good. So from myself and from my entire group, I want to thank His Highness for all the constant support and encouragement. And these are the two students who mainly did the work that I explained, that I showed you here. And let me thank also some other funding agency from the Indian governmental agencies. So with that, I'll stop, and I'm happy to take any questions that you have.
Thank you, Bivas, for that excellent talk. And are there any questions or comments? Please, microphone is here.
Really nice talk, Bivas. I just wanted to know about the scandium nitride. You could change the carrier concentration quite a lot in that, but I missed how you do that.
Oh, yeah. So scandium nitride just is 3,5 semiconductor. So when you don't dope any hole dopants, because of the nitrogen vacancies and oxygen, it shows high carrier concentration. So when we want to reduce carrier concentration, we basically dope magnesium, and magnesium is an extremely good hole dopant, so that can reduce carrier concentration very effectively.
Another quick question. Have you ever looked at any oxides for plasmonics? So strontium molybdenate, for instance, that's quite an interesting material.
Yeah, I mean, as a group, our group in JNC, we haven't worked on oxides. When I was a student, I used to work on this transparent conducting oxide and try to make them plasmonic in the infrared spectral range, near infrared spectral range. For example, ITO, aluminum dope, zinc oxide, GGO, gallium dope zinc oxide, things like that. Oxide can also be extremely important and interesting plasmonic materials, provided you control.
There's a lot of work to do, isn't there, on them? There's a lot of potential.
Yeah, absolutely.
Thank you.
Are there any further questions or comments? Tony, please.
Yeah, thank you very much, Bivas. a really interesting talk. I wanted to ask you about the last part of it, this paint, this sort of reflective paint. Do you have any sense of how durable it is with the polymer and so on?
Right. Yeah, that's a very good question. See, for a reflective paint to do its work, there are many properties it has to satisfy, not just optical property. It has to be wear resistant, tear resistant. It has to be good adhesive. So we haven't looked at that, honestly. But we are planning now to incorporate adhesive in the paint itself so that it sticks to the surface much more and test its endurance properties. In fact, day before yesterday, we had a discussion about how to proceed on that, but that part is still remaining. That's it.
Good, thank you.
Thank you.
Okay, are there any further questions or comments? If not, I'll ask the last question maybe. Then how do you get around the free carrier absorption loss in these materials?
Yeah, so that's a good question. So if you are using the visible spectral range, then you have to dope carriers, and carriers will give you absorption in the infrared spectral range. But if you focus on visible spectral range, that's not a problem. So, that you're fine with that. Similarly, if you look at the infrared spectral range, the region of our focus, their free carrier absorptions is, free carriers basically give you this transition, but absorption is not that high. It is within the limit of less than 1 or less than 1.5 or 2. But there is this inherent trade-off that you've highlighted that is real. You really can't get around it. If you need carrier to generate plasmons, it will also absorb at one point. Yeah, I totally agree with that.
Okay, on that note, could you please join me to thank Professor Bivas Saha for giving a beautiful talk?
Thank you. Thank you.